Hello, welcome to this presentation. My name is Yuwei. I am a PhD student from Télécom SudParis and cooperated with the company EDF Lab France. Today, I'm going to present my early research achievements paper titled Runtime Models and Evolution Graphs for the Version Management of Microservice Architectures. As we know, recently the information systems in industry company has a trend of migrating from monolithic to microservices as a set of independent functional units. In the ecosystem of these industry enterprises, microservices of an application are usually developed and maintained by different internal teams or subcontractors without a global governance. In addition, microservice providers often deploy multiple versions in parallel, offering some specific versions to certain customers or older versions for legacy systems. Of course, not all the microservices involved and are upgraded at the same rate. In this case, the updates of these microservices add dynamics and complexity to reconfiguration deployment. In our work, we demonstrate our solution with an illustrative application that includes 5 microservices. A simple scenario of our use case is displayed here in the figures. That authentication service changed from version 1.0.0 to 1.1.0, and a logger service is added to communicate asynchronously with other microservices. In this context, our proposal addresses some typical requirements identified in industrial contexts and by software architects. On the one hand, when involve and maintain the different software solutions, the industry company should rationalize the cost. So a global view of this ecosystem evolution is necessary, and the evolutionary changes in the information systems should be traceable. On the other hand, software architects need help to model evolving microservices in a uniform manner and to facilitate to take decisions dynamically on version changes while the system is running. And then, after decisions taken, another issue comes concerning planning and executing automatically the redeployment of changed microservices. So we follow the MapK approach of causality between the control loop and the managed system for autonomic computing. We consider our proposal is semi-automatic. That is to say, the decision of version changes are made manually by architects, and the activities of planning and executing are performed automatically. And in this paper, we mainly focus on the part of knowledge base. Therefore, based on some recent works, we propose 2 main contributions in this paper. Firstly, we talk about runtime models. The first existing proposal builds a microservice evolution model by observing the managed system under execution. It includes versioning of some of the model elements, namely application, service, and operation. This work focuses on synchronous communication. Then, another model in the second paper here is derived from a specific ecosystem of microservice technologies. It considers interactions using RESTful HTTP and MQTT protocols, but it has no version information in model elements. So we propose our runtime models to represent the versioned up-to-date elements of microservice architectures. Our model separates the view of type model from the instance model and exposes the conformity between the two models. We also give a more complete point of view of different communication modes, including client-server and publish-subscribe. Secondly, we talk about evolution graph. The first existing solution tracks microservice dependencies and versions by analyzing code and runtime entities. The dependency graph was computed through a series of chain search, and version management was based on chain manipulations. Then, in the second paper, the authors create a version timeline for each microservice that includes version dependencies to record revision histories. So, in our proposals, we record the trajectory and history of how the system evolves over time. We build up an evolution graph, and each node in our graph is a snapshot of the running system configuration as version changes are applied. In our work, the dependency graph is included in the model, and version management is based on model element manipulation. And we trace evolution histories from the point of view of configuration that is a set of microservices, not just a single microservice. And now we enter into more details of these two contributions. For the runtime model, the model of types captures the structure of instantiable elements of the involving microservice applications. All the types are uniquely identified by an identifier and a version. Any version change of a microservice creates a new microservice type with the same identifier but a changed version. Each microservice type exposes a set of contract types that are the interfaces providers or required. We model for synchronous communication of request response on the right and asynchronous mode of channel-based or topic-based publish subscribe on the left in this diagram. With this model, every time types on which versions are chosen by architects and the change of current configuration type is committed in the type model, the property of is instantiable will check whether an instance model can be created that conforms to these types. Then, here you can see the model of instances. It captures the replicates of deployable elements of the managed system. Each instance conforms to a type in the type model. Similarly, whenever there are changes occurring in the current configuration, architects can check whether instances are deployable. Based on the runtime model, an evolution graph is built to show the evolution trajectory of a microservice-based application from two points of view of configuration types and instances. When version changes are adopted in the code base, architects take a sequence of change actions in the type model, such as adding a new microservice type or a new connector type into the current configuration type. This created a new node of the next valid configuration type to commit in the evolution graph. Each node of a configuration has a unique link to a configuration type. In the figure, the graph has several branches, for example, for the abandoned node, and it is possible to roll back to another valid node. Based on our proposals, but not presented in this paper, we have engineered in a prototype of an AI planner compute a plan of actions of reconfiguration and an executor for automatic deployment. To conclude, we have discussed how our proposed runtime models and evolution graph help engineers manage microservice versioning, abstract architectural evolution, and perform reconfiguration deployment. The prototype that we have implemented, called Mimosai, can be found on the website here. In our future work, we will study on the continuity of microservices while applying the dynamic changes. That is to say, when the update of microservice can be performed in a safe way and how to keep the system consistent before and after runtime changes. This is a brief summary of our work in this paper. Thank you for your attention to this presentation.